So I appreciate everyone's decision to sit here and listen to me instead of swimming outside. Now, first the question, who is interested in mathematical backgrounds of predictive modeling of complex production processes? Yes. But still, okay, then who wants to see less harmful waste deposited in our environment? Okay, perfect. Then you're at the right lecture. No? Okay, we have to discuss this later. Anyway, I will discuss the glass manufacturing process and the waste that comes out of it and how we could establish a circular production loop. What we are dealing with is a furnace shown here. We have a glass melt, a pool of glass melt over here, and a channel that takes this molten glass to the bottle making machines. Here in the back we have two such pillars that are used to harness the energy of the heated up gases, and this is used for preheating the gases that go into the chamber, into the furnace. And we see this is one exhaust pipe. Here behind here is another one, and these are the burners. And the side of burning is changed every 20 minutes. So this is to capture this energy. This is how a process, a scheme of a process looks like. So we have a glass melt. We are feeding raw materials inside. We are pulling glass out and making bottles. What is left, so flue gases are leaving the environment on top of the glass melt and are going through heat exchanger, then to a filter, electrostatic filter, and here we have filter dust that needs to be disposed of. So typically 300 to 400 kilograms of such dust is collected, and this dust is harmful. Now, an idea is, would it be possible to capture this dust, measure its chemical composition, and return it as part of the raw materials back into the furnace and burn it again? Now, why would one want to do this? Let's look at the background. Steklarna Hrastnik is producing glass bottles. Okay. Now, there's nothing special about glass bottles. Almost everyone can do that. But the specialty of Steklarna Hrastnik is the type of glass that they are using. And this is called extra white flint glass. And so what does this mean? It means that it's extremely transparent, so a lot of light goes through this glass. So some of it is absorbed, and what is absorbed should be absorbed equally across the whole spectrum. Mm-hmm. So glass is transparent, it's not yellow, it's not green, not pink, you don't see it. How do they achieve that? In raw materials you have some iron present, which you cannot get rid of. And in order to compensate for the green color that would come from iron, you add selenium oxide, and this brings pink color and neutralizes the green color from iron. Okay. Now, selenium oxide is a very specific type of, it's a very, let's say, peculiar oxide. It's very highly volatile at these high temperatures which you need to melt the glass. So about 60 to 80% of what you put into the furnace in the batch gets lost through the chimney. Okay, it's an expensive raw material, so it gets lost through the chimney. It gets, of course, captured in the filter dust. It doesn't go into the environment. And because of the high selenium content of this filter dust is then a hazardous waste, right? So you need to pay a lot of money to get rid of it. and it's not good to have it in the environment, of course. Now, if the company would want to recycle, like put this filter dust back into the furnace, they would need to really know very precise content of selenium oxide. Otherwise, their glass could be pinkish or green, right? So it's very mandatory. But now the chemical analysis of this filter dust are taking a long time and are expensive and are also dangerous because of some byproducts that happen during the chemical digestion process. So we have thought of an alternative. What if we could use the production parameters of the furnace, temperatures, flows, amount of energy going in, and make a mathematical model that would predict the amount of selenium oxide in the filter dust, right? And use that prediction to feed the powder back into the furnace. And yeah, we did just that. I will present you how this was done. But now let's see the manufacturing process of glass is a continuous process, and we have sensor readings based on, so each minute lots of sensors are being read. There are more than 40 online sensors that are measuring various temperatures, gas consumption, and other things. So this is how the process unraveled. We first took a look at the historical process data to see what we are dealing with, what are the periodics and so on. Then we had lots of discussion with subject matter experts. So these are the people who know the process very well, because they are an invaluable source of, a very valuable source of information, right? So that helped us to design dust sampling procedures and the analysis. So we have sent dust to be analyzed at a German institute. Then we have created a simple mathematical model, took a look at it, saw that it needs to be refined, and then we refined it very cheaply, as we will see. And then we have validated that model. Okay. Initial data collection and screening. This matrix is showing you lots of different parameters that are being measured, and we see lots of them are correlated to each other. So we have first reduced the amount of parameters that we will use for modeling by eliminating those that are highly correlated. So we had lots of data, lots of discussions, and so on. And here is an example of process data for a few parameters for 1 day. So this is 24 hours. And we can see some of them have very high variability. And this comes from this turning of the sides in the thermal recuperator. And this had to be taken into account because selenium is being evaporated on top of the melt and is going through, and how it is captured in the filter dust. This variability was very important in the end. We have checked the so-called autocorrelation. We did the periodicity analysis, which is fast Fourier transform of the data, and we saw at 41 minute mark, we have a very strong signal, and this is exactly this changing. So 40 minutes is one cycle, left burning, right burning, and then back to left burning. And this can be very nicely seen on the data. We have checked the autocorrelation and the stability of the process, and we saw that the process is stable. We can work with that. Then dust collection plan. So experts had some knowledge from before, and they said selenium content in filter dust is mostly influenced by the glass pull rate, so how much glass we produce per hour. Okay? Then we checked the glass, the production plan for the next month, and we have determined some middle values for plant production, and then minimum and maximum to cover the whole range of production So then dust was collected in these 20-minute time intervals, and it was homogenized. After homogenization, we have sent it to external institute for analysis. ICP-OAS was used. And here a very notable mark. We simply were not able to determine a very rigorous procedure where staff at where operators, where process operators or keepers of the line would be extremely cautious about different influences that could contaminate the glass, or that the filter dust, or that the filter dust was mixed very well. So we took a decision, and then we personally went and collected the dust and homogenized it, because we thought it's the crucial step in the process, and if we would later on not be able to trust the data, then we would always, be questioning what if something went wrong with the dust sampling. So this was I want to emphasize here that whenever you're doing any such experiments, and so it's very important to identify crucial points and have control over them, right? So we did that. This is my colleague Drates. And then based on these 9 data points, so 9 data points from 20-minute sampling, from ICP-OAS analysis, plus 5 data points from various big bag sampling, but with much less precision, we have created a simple mathematical model where with only 3 parameters: natural gas flow, glass pull rate, and power on electrical heaters. Okay. So this is at different dates. This is showing the values for each of these 3 parameters. So we can see we have some minimal values, some middle values, and some maximum values of these parameters. Okay, we have built a mathematical model. Here, during each 20-minute sampling time interval, we can see different parameters are changing in their values. So they are not fixed like this one, like pull rate, for example, but some of them have very high variability, some changing curves. I will show later how where this is important. So a simple model looked like this. On a first glimpse, one would say, okay, this is a really good model, has very nice actual versus predicted plot. Mean power seems to be the most significant parameter, then some others nicely sorted down. But when we dove, when we checked this model performance in more details, we saw that, for example, the connection to mean power is not physically sound. It's counterintuitive, and it doesn't follow the physical principles. For example, if mean power goes up, then this graph is showing that the selenium oxide would go down in filter dust, which is not true. So the model looked good, but it was making physically strange predictions. So it was not good, not fit for use. And then we brainstormed what is going on. So of course, this model was based on only 3 parameters, which means for sure there are much more influential parameters in the furnace and need to be included. But we only had 9 reliable measurements. So how to include more parameters with so little measurements? So then we said, okay, we have to expand the data set in order to use neural network for modeling such behavior. But how do we do that? So if, I mean, you can always do additional measurements, right? Collect the dust, homogenize, send to an external institute, but this takes a long time and it's expensive. Is there a cheapest way is there a cheaper way to achieve such thing? This is always a question in our society and, of course, in life. So we have come up with an idea that we would add information to data set from this 20-minute sampling interval distributions. So during 20 minutes of sampling, we saw some parameters were changing on some curves. And in the first model, we have only used the mean value per interval, right? So we said, okay, let's use Monte Carlo approach to pull individual values out of individual parameter populations. But now there is a problem. Some parameters are highly correlated one to another. So if this method would pick low value of some parameter, if some other parameter is highly correlated with the first parameter, then we should always ensure that also the low value of the second parameter is chosen randomly, right? And not some completely random value. So this was very, very important. And together with process experts, we have then considered 13 input parameters. So we have reduced this from 40. We've came to 13. And we used Monte Carlo simulations, and we considered parameter correlations via so-called covariance matrices. So for each of those sampling intervals, we have created such matrix. This is a covariance matrix, and it tells us how much different parameters are correlated. This is evaluated numerically. So +1 would mean they are absolutely perfectly correlated. -1 would mean they are completely anti-correlated, and with values in between those. So we have created such matrix for each of those 9 data points, and then we did we used Python to generate multidimensional normal distributions where we took covariances into account. So these are covariances. And this is how our new data set looked like. So we had clusters of points. We had 500 points per sampling, as opposed to 1 data point per sampling from before. So the new model looked much more complex. We see much more complex behavior. So if this is predicting the amount of selenium dioxide, and these are individual parameters, we can see that the relationships are not linear, and there are probably also lots of interactions between parameters in here. So we can see much more complex responses, and we can also predict the shape of the histogram of selenium dioxide emitted in content. Now each model has to, of course, be validated before we can trust it, and we did just that. So the blue points here represent the training data. So these are the points that were used to train our model, and the red points are the validation data. Here we can see the 2 points are standing out, and actually we have been expecting that we will see these 2 points in some distance from the model, or far away, because there was an issue with the big bag here, and the plant staff, they actually didn't know if this is the right big bag or not. So we still included it based on hope that it is the right Big Bang, but it might not have been, right? So all others seem to lie very well on the actual by predicted plot. And in order to validate the procedure, actually to examine the quality of the procedure with the use of covariance matrices, we have also tried Monte Carlo simulation without the covariances, and this was the result, right? So if we compare both models, this one is with taking covariances into account, and the red one with much larger scatter is showing the model performance if covariance matrices are not observed, are not taken into account. So as a conclusion, even though we had very little amount of data points, still a seemingly useful model was created, and the approach resulted in a 100% return of the waste filter dust in a pilot attempt. So this was some limited time where this was tested in the plant. And this replaced about 60% of expensive primary raw material, and in the end it led to a zero waste production. Still, this was a limited time frame where this approach was tested. Now company is interested in bringing this to a larger scale, but this requires lots of hardware for mixing of powder dust from big bags and different transport procedures and so on. So yeah, that's all. Thank you.
Thank you. So, do we have a question from the audience? It's such a complete story that no questions here, obviously. Yeah, obviously you choose the right approach using the covariance matrix, as we know.
Yeah, it seems so, yeah.
Because mathematics is not always taking the physical reality into account.
Yeah.
So it's nice. No question? Yeah.
Yeah?
Yep.
Thank you for a very good information. Just thinking, this was the return to the production due to the selenium oxide. What about the other components of the that was to them? So are they also reducing maybe the other inputs of the raw materials, or they just go through like?
Yeah, very good question. So the question is related to if a circular loop is established, what is happening with other elements besides selenium that are also in the filter dust? And this is, of course, a very, very important question, because some materials could start to get, some elements could start increasing in the content value. For example, mercury could be one of those. Because it's even more volatile than selenium, and it gets captured, right? And if you establish such a loop, mercury will not go into glass, and it is coming inside from raw materials and maybe from some scrap if they add it. If you introduce such loop, then you're actually refining mercury, right? You're increasing the content in filter dust, and this filter dust may become even more harmful in the end. There are some other elements, but they're probably not that important, because this filter dust mostly consists of some sodium, calcium oxides, and so on. But in order to ensure the stability of dust, or to keep the harmful substances low, I think the general approach, based on experts from the field, we have consulted, for example, Professor Conrad from Aachen University. He's an expert in glass, And he mentioned there's no other way basically than to just regularly do chemical analysis, not very often, but still here and there, and see what's going on in the dust. And if certain values would increase, then there's no other way than to still keep that filter dust from those events, or every now and then, keep that dust and still dispose it, or refine it, or somehow. I don't know. This is beyond my understanding. Thank you.
So at least some cycles you can repeat and then throw away.
Yeah, they're always, but still, if you need to dispose of 1 month of production instead of 12 months of production,
exactly.
It's still
it's a way to reduce.
Still benefit,
If it's zero, it's even better. Okay, thank you once more, because again,
thank you.
Right?